The purpose of this lab was to predict the behavior of circuits containing resistors, use multimeters to measure values of current and potential difference, and examine the behavior of ohmic resistors and capacitors. To explore these behaviors, I used real circuit equipment, including multiple multimeters that describe parts of the circuit. Some key concepts that I used for this lab include the current node rule, which states that the electron current entering a node is equal to the electron current leaving a node in a steady state. The loop rule, which states that the potential difference of a round trip in a circuit is zero. In the end, I found that I could use laws of circuits and knowledge of potential difference to describe the behavior of real circuits. For the first part of the experiment, I constructed a system containing two 1.5 volt batteries, wires, a 100 ohm resistor, a 47 ohm resistor, and some multimeters. When recording the current on the ammeters, they both read 20 milliamps or 0.02 amps. By reversing the connection of the multimeter, it then read negative 19 milliamps. By changing the setting on the multimeter from milliamps to volts and attaching it to both ends of the combined batteries, it then read 3.2 volts. Next, I checked the potential differences between different smaller segments of the circuit. From the batteries to the 100 ohm resistor, the multimeter read 3.1 volts. From one end of the 100 ohm resistor to before the 47 ohm resistor, it read 2.1 volts. From one end of the 47 ohm resistor to the other end, it read 0.7 volts. From there until the batteries, it then read 0 volts. Using these values and the current I recorded, I could calculate the measured resistance of the resistors. The 100 ohm resistor had a measured resistance of 105 ohms. The 47 ohm resistor had a measured resistance of 35 ohms. For the next part of the experiment, I constructed an RC circuit, which is a system containing two 1.5 volt batteries, a capacitor, and a light bulb. When the batteries were connected with a capacitor and a light bulb, the light bulb would light up and fade over time. This showed that the capacitor was charging. When the batteries were disconnected and the capacitor was connected directly to the light bulb would again shine and fade out. This showed that the capacitor was discharging. I repeated this process with a 10 ohm light bulb and a 20 ohm light bulb, and timed the charge and discharge periods. For the 10 ohm light bulb, the charge time was 11.98 seconds, and the discharge time was 14.61 seconds. For the 20 ohm light bulb, the charge time was 60.49 seconds, and the discharge time was 51.09 seconds. Using the voltage and time data that I gathered from the experiment, I created two graphs representing a linearized version of the decrease in voltage over time. The slope of the graph is equal to the negative of the reciprocal of the RC constant. For the 10 ohm light bulb, I measured that the RC constant was 4.5, and for the 20 ohm light bulb, I measured that the RC constant was 42. In this experiment, there are many possible sources of error. The multimeters used for the lab were at times faulty, leading to possible incorrect measurements. They and the wire have a non-zero resistance, while in calculations a zero resistance was assumed. And the time to start and stop the stopwatch in part 2 could have been imperfect as well. What if I charged the capacitor with no resistor in the circuit? In an ideal circuit, the capacitor would charge almost immediately due to the unrestricted speed of the electrons in the circuit. This ideal situation would not happen in real life, as the wire and the capacitor have a small but non-zero resistance.